Hello. In this video, we're going to be showing how MQ can be configured to provide service and message availability when deployed across two data centers, ensuring messages are never lost, service continues unimpacted, and messages can be made available as quickly as possible during client or queue manager outages. In our setup, we have simulated two data centers running across two cloud or on-premise deployments. We have a dashboard, which is simulating mobile phone users, and we are imitating making payments. To do this, we have three services: balance check, fraud check, and sanctions check. Each service has their own MQ queue manager with identical deployments of MQ and MQ clients across both data centers. We push messages evenly between data centers, assuming they are available, and all the queue managers are in a connected MQ cluster with a full repository in each data center. This means traffic can continue processing even if we have a client or queue manager down. On each queue manager, there's an MQ service running, which is a sample program provided with MQ. It monitors queues in the cluster as defined in a cluster queue list. The dashboard shows which route the messages took through the MQ cluster, as well as how long it took the end-to-end journey. It is expected that in most cases, messages will continue to be processed and will be completed within a 30-second delay time. Often this is much quicker, but in some cases where messages are stuck on queue managers, we don't lose messages, they are simply delayed. The dashboard will show this as we run through our failure scenarios. In the following failure scenarios, we are going to show the outcome of simulating a client outage, simulating a queue manager outage, simulating multiple client and queue manager outages, and simulating a complete data center outage. In our setup, we have our three clients running in data center 1 and in data center 2 on the first and second rows respectively, and we have our mobile app simulation, which is going to send 150 messages through our MQ cluster. During the run, we are going to end the clients running in data center 1. And then recommence them. Next, we are going to kill two of our queue managers running in data center 2, simulate a queue manager outage. We can see that during normal operations, we have relatively quick latency. When we see the client stopped, we see more traffic running through the alternate queue manager as messages are moved by the cluster queue monitor utility. We also see that during the queue manager failover sequence, there is a short outage while the RAFT consensus renegotiates the primary active instance before processing continues. This results in messages on the queue manager at the outage time being slightly delayed, which has a higher latency. We can show multiple outages across the stack during normal operations. In this example, I will stop two clients in data center 1, failover one queue manager in data center 1, and failover one queue manager in data center 2 during the pushing of the 150 messages. I will then restart the two clients in datacenter 1. As we can see, messages might get delayed, but do not get lost. When we see a data center outage, we expect that messages already on that queue manager will be stuck on the queue manager until the data center comes back up. Or if we use cross-region replication, we can access messages in the other data center. In this demo, we will show messages being stuck but being processed when the cluster comes back up, allowing businesses to gracefully process them, either running them late or ensuring no transactions were lost. To simulate the outage, we are going to stop all network traffic across the MQ namespaces in one of the data centers. As we can see, we are starting to get some errors when attempting to push to data center 1 due to the network policy. I will now remove the network policy to allow traffic back through to data center 1. As we can see, messages might be delayed, but do not get lost. When we killed this client, we saw the cluster queue monitor transfer to the second site via its logs on the queue manager. In the dashboard, we saw slightly longer latency, and we saw more traffic processed by site 2 when originating in site 1. This shows the cluster is rerouting traffic and stuck messages are continued to be processed. When we killed the queue manager pods, any messages on the persistent volume are retained, but we saw larger delays as the consensus selected a new primary instance. This was visible in the dashboard with delays of 70 to 100 seconds. When the cluster was down, we saw this happen at a larger scale. Messages were stuck on the queue manager. We have shown that we can withstand service outages of individual components, such as client and queue managers, and while some messages are delayed, we do not lose messages. Thanks for listening. If you would like advice on how to improve your MQ resilience, get in touch with your IBM representative for some Technology Expert Labs advice.